Okay. So thank you very much. Afternoon, all. This is Wolfgang Stautner from GE Research, and let me first thank Professor Ali Genscher and the ICSM conference team for inviting me here for a talk on recent advances in cryogenics, from applications to materials. So here's a view. Let me just introduce ourselves. Here's a view of one of the main buildings of our General Electric Research Center based in Niskayuna, New York State. Located on the Mohawk River, there's a long history in superconductivity and cryogenics. This briefly shows our capabilities and breakouts driving us from research to reality. We are shaping the future of flight for emission reduction. We are advancing our healthcare portfolio and lead the energy transition for the renewable industry, to name just a few. On this slide, I'm sorry it's a bit crowded, we show our previous work on superconducting technology that started way back in 1963. And since then, we built quite a few generators, 1.5 megawatt high temperature superconducting generator in 2003, and hydro generators that was completed in 2012. We pioneered in AC homopolar inductor alternator designs for using HDS conductors in a high-speed megawatt high-temperature superconducting generator with the US Air Force, which ran at 10,000 RPM and delivered 1.3 megawatts of power. And what people probably don't know, we actually manufactured and supplied the first superconducting niobium tin tape to Sir Martin Wood of Oxford Instruments, who then created the first superconducting magnet in 1965, reaching 10 Tesla. And you can see about the radial dimension here on that axis. So, since this is mainly a conference on magnetism and superconducting technology, I will take the opportunity here to give a short intro to the world of cryogenics, which, by the way, is not always an easy one for engineers. And together, we will cover today advances in cryogenic applications and components, and end this talk with a summary and an outlook. It has to be said, however, when I look back for the last 45 years, it has to be said that progress in cryogenics is rather slow. So what is cryogenics? Cryogenics is the branch of physics that deals with the production and effects of very low temperatures. Now, where does cryogenics start temperature-wise? Well, now, it is really the LNG temperature of about 111 K. And below that, we tend to talk about cryogenics. And above that line, we talk about refrigeration on the right. The box chart top and bottom shows the temperature of the cryogen at its normal boiling point, whereas the lower one refers to the melting point. And note that helium does become solid under standard conditions. Also, please mind the gap here between neon and nitrogen, that is between 27 and 77 K. This gap can, to some extent, being bridged using gas mixtures. So you may have seen this plot already from Seat Melham on Sunday, It shows the historic drop of resistance of a mercury wire in Ernst's lab. This figure is particularly of interest to cryogenics, since to get there, he first had to find a method of liquefying hydrogen. After he managed to do that, he then used hydrogen as a pre-coolant to recondense helium. Only then he was able to show this result. But already back in 1911, it was quite clear that this phenomenon can be commercialized. And here's one of his sentences: some such apparatus could be made at light near modest financial support were obtained. So he was already planning of making and creating a magnet out of it. The Nobel Prize, however, was awarded for the technology to liquefy helium on a production scale. Now, this is a recent plot that shows where we are on critical temperatures for superconductors. And note there is still a similar temperature gap between Mgb2 and YBCO as we have just seen in cryogenics. I will not go into further detail here, since we had, as you recall, the plenary talk yesterday from Professor Akimitsu on this topic. Yeah, superconducting technology needs cryogenics. We still need to facilitate a cryogenic environment despite some efforts towards room temperature superconductors. And as we shall see in the following, the comment on superconducting applications from Powell says it absolutely clearly. For superconductivity to be successful and making it into a product, it must offer significantly better performance and/or costs than alternative traditional methods, as we shall see. And just looking back for a moment on the cryogenic landscape, what it was in 1975 by Kobayashi, and the roots are shown here in the bottom, but this tree has grown quite a lot since then, and even a bigger branch here has evolved due to the discovery of high-temperature superconductors. So all you see here are potential applications that keep that tree growing, and that this kind of branch actually merged into a new tree. It grew into a new tree that has developed new branches and new applications. Yeah, but the roots may be the same, but the temperature range for this application is now above 20 Kelvin, and many new applications can be seen on the horizon. So when did it all start? And well, let's look of how we did in commercializing superconducting technology. And I think that is really important, and having witnessed that myself, it's quite interesting to see that the center column that shows what the researchers working on superconducting applications believed their prototypes would make it commercially. And the right one is a new estimate. So most of the technologies were meant to be within reach at that time in 1973. But also note that, fortunately, applications did evolve that weren't predicted and unknown yet in 1975. For example, superconducting workhorse, MRI for healthcare, and NMR. But you can see there's a big disconnect here, and it was a big disappointment. I really recall that myself, how everyone was going into superconducting, many superconducting applications, and trying to commercialize, but it just didn't happen. Now let's look at the advancing cryogenics for MRI. And as you may already know from Siad Malham's talk, we use quite a big chunk of liquid helium for MRI systems, which is around 30%. And what we also learned back in 2000, the cost of helium is really, really unpredictable. So why is that important? Just look at a cross section of an early MRI magnet that shows the superconducting coils immersed in a large helium tank with a liquid nitrogen tank as well. And nowadays, the fill volume is about 1,500 up to 2,000 liter. But before 1996, however, there was no suitable cryocooler that actually could recondense helium. So the boil-off of such a system was really huge, in the order of 1 liter per hour. Basically unsustainable, but there was a huge pressure also on the cryogenic industry to come up with some novel ideas on recondensing. Here's one of the most recent 3 Tesla MRI magnets from General Electric. It's a patient bed. And let's have a closer look what's inside. And that's a cross section through that MRI system. Here again, you can see superconducting coils immersed in liquid helium, and you can see here is this cryocooler. And you may notice that there is a recondenser here. And in 1996, GE, together with Sumitomo Heavy Industries, developed a cryocooler that was capable of liquefying helium. However, it was quite a long path since the complete cryostat had to be redesigned for the cooling power that the cryocooler provided. So the figure shows the coils immersed in liquid helium. And you may not be immediately aware of it when you take an MRI scan, lay on a table, that the distance between room temperature and 4 Kelvin is only 2 centimeters. So here's the interesting story. Around 2003 and 2004, a breakthrough happened in cryogenic technology on some early MRI prototypes. And the extensive research on thermosiphon technology at that time enabled us to reduce the 2,000 liters of liquid helium for operation, and when being shipped to a customer down to 30 and 40 liters. And now here's the thing. But to develop that and to make it into a solid product, it took almost 20 years. But this is one of the biggest achievements of the last 2 years. And we're currently selling around 40,000 MRI systems. This shows one of the new magnets with this recent technology that was installed at Rochester. I probably should say that the helium vessel, that is all what is left as a helium reservoir in here. So this shows one of the new magnets with the recent technology that was installed and shipped to Rochester. Is mainly for concussion research and other brain research related problems. This slide shows a few important design characteristics that should be implemented for future MRI systems, and it making MRI more affordable. So there's plenty of work to do, make MRI more user-friendly, and extend the MRI technology, of course. I won't go into detail here, but this was the cryogenic roadmap I want to highlight again, that led to the massive helium reservoir reduction. And note that we are not at the end yet of what we can technically do. And most likely, the goal most likely is not to use any helium at all. So it all started basically in 1980. As we go to higher superconductor temperatures, we may move away from helium and at least partly replace helium with hydrogen. The MRI history is really fascinating, since it is one application that made it commercially with superconducting magnets and cryogenics complementing each other. Now let's look at what is going on in aviation cryogenics, which is an entirely new topic here. And as you have heard, for tackling and reducing carbon emissions, we now need to develop all-electric cryoplanes based on superconductivity and cryogenics. This is a very important project here that shows the feasibility of this technology. We use liquid hydrogen tanks and a cryogenic infrastructure throughout the plane. And here you can see the propulsors. This is what it looks like. That shows the cryogenic architecture for mid-range and long-range aircraft using green hydrogen. There is a pump here required, a liquid hydrogen pump required. And this architecture includes superconducting motors, superconducting currents leads, superconducting transfer lines, superconducting power electronics, which is an entirely new area here, and fuel cells. If you want to learn more about that, there are some good publications I can recommend that have been downloaded many times. So what is a superconducting machinery cryogenics look like? Well, we have these different types of cooling modes: bath cooling, thermosiphon cooling, forced flow cooling, and of course conduction cooling. And the cryogens in question to cool those high temperature superconducting applications are the same. And for those that we identified earlier on, here's a completely novel cryogenic design that uses cryo-coolers for a thermosiphon cooled system. The thermosiphon is somewhere around here, the coil. Condensing neon on a so-called homopolar machine for airborne application that we developed quite successfully. And the novelty here was that we can show that a very few low-power Stirling cryo-coolers suffice to liquefy neon into a thermosiphon and maintain cryogenic temperature stability of that superconducting coil. Here are some further examples from GE Energy from in which way cryogenic technology recently progressed to develop remote cooling options. So this is a generator, for example, but the cold box is quite separated from it. This means novel cooling options that are not very close, they're even detached from the superconducting generator cold mass. Here's yet another example from GE Energy in which cryo-coolers, you can see them here, and impellers are fitted in a cold box that then transfer helium, compressed helium, through a cooling tube to a superconducting generator. The coil on the right here that I'm showing with my cursor shows the cooling light that is being fed from this cold box to maintain a temperature of approximately 30 Kelvin. This is a depiction of a recently emerging general trend on advanced cryogenic cooling for many superconducting applications like superconducting cables and so on. The basic principle is always to use turbines or impellers coupled with a cryo-cooler infrastructure, similar to what I've been showing in the last slide. This slide now gives a summary of typical cryogenic technologies that recently evolved for various applications. And at the moment, what we do in generators and motors are of particular interest. And this slide shows which cooling solution can be used. And of course, there's always more work that needs to be done to increase mean time between failure. Just one comment here. I've often been asked what actually is the benefit of 20 Kelvin cooling versus full cooling. Well, it is a big change indeed. First of all, we benefit from an excessively high cooling power that is available now at 4 Kelvin. That is a big change indeed. And another benefit is the cryogenic coupling to a cold mass that is now much easier. And the warm-up time as well of the cold mass is much longer at the power outage. And the thermal conductivity of cryogenic materials is in an order of magnitude higher than that at 4 Kelvin. And last but not least, I can create a more compact, low-weight design for most applications, just to name some of the few advantages. Another application that needed a completely novel cryogenic approach was for the renewables industry. As you may have seen in the news, on the left is the largest wind turbine you can make conventionally today before moving to superconducting technology with higher power densities. And here is shown one about the high temperature superconductor, 3 megawatt class, and here high low temperature, high power wind turbine design, an early one. Did we see any advance in cryogenics on accelerators and detectors? Yes. And so one good example of how the novel cryogenics helped to stabilize and maintain this large system for the CMS muon detector was by utilizing thermosiphon technology. You can see here the cooling lines and the cold box on extremely large scale. The diameter is about 6.3 meter, very similar to what you have seen at a much smaller scale for advanced MRI units that were showing in earlier slides. Jumping now to fusion, how did the cryogenic cooling of fusion magnets evolve and from? And this graph shows you the development starting in 1951 with a conventional stellarator up to future ITER. And marked in between, there are these historic technology breakthroughs. When you now look on how those units were cooled, you will notice that they all initially started with pool boiling or as immersed systems, just like MRI units that I shown earlier. However, it needed a big capital investment on cryoplants and liquefiers. And here is one of the early pool boiling systems. I happen to be standing next to it. So you've got here this helium dewar, and that helium dewar feeds down into the D-shaped coils and back and boils off here. So that was basically the principle at that time. Now this is again an interesting slide that shows the slow, really slow technology transition from pool boiling to forced flow boilings that happened to some degree in 1984. And since 1994, all those coils are now forced flow cooled. However, this requires an internal cooling channel close to the superconductor. Here's one of the earlier Supra systems, 1988. And here's one of the ITER TF coils, one of the latest pictures. So when you then compare the different cooling strategies for fusion and how they evolve for supercritical and coolants with advantages and disadvantages, and how advanced single-phase helium cooling emerged for new fusion systems. And this is basically where we ended up. Yeah, with a lot of advantages versus two-phase helium flow. Here's an example from GE Power and of Alstom Belfort, who contributed to the JT60 program, and that is a satellite for ITER. There's a total of 18 toroidal field coils. And here's a nice picture that shows the insertion of one of these field coils into the system. And that's a view on how the last coil was inserted before completing the tokamak. Now let's recall the earlier point I was making about commercialization. And here we are talking about commercialization of fusion systems, which is a completely new dimension of challenges. And we learned how to use cooling channels for low temperature superconductors, and that was showing earlier on. But now we can apply that to high temperature superconductors for fusion as well. And here are some new pictures of how that can be done, where we have cooling channels through the superconducting matrix, with either in using that whole space or having a separate cooling channel. So it can be really cooled with different conductor configurations. And here's a nice example how Repco conductors will be cooled with liquid or supercritical helium, almost similar to what we know about low temperature superconducting Rutherford cables. So now here's a cooling channel. Sorry, I forgot to mention that. Yeah. So this is Repco, and it's really, we are really taking advantage of what we've learned from low temperature superconductors here. We also talked briefly about next-gen compact fusion magnets already in this conference, so let's briefly touch it again. You may have seen that from Siad's talk, and I don't need to repeat it here, but just to remember for now that we need at least 10,000 kilometers of high-temperature superconducting wire in the near future. And it also shows that the fusion magnet size reduction as the field increases, as you would expect. Here is a summary slide on how high-temperature superconductors can play a role on smaller fusion systems for tokamak energy. I added here a general slide that shows the conductor types for different HTS applications. And you may recall what I said earlier in terms of wire length requirement. For low temperature applications, as a comparison, we currently produce 300,000 kilometers of wire per year. So it is quite a striking difference to HTS. We are now diving, let's shift gears a bit again, and we are now diving deeper to the cryogenic component level on materials, and in particular mention a very important insulation, what we call multi-layer insulation, or in short, MLI. And let's assume that we do have specific thermal losses on a system here for an MRI system that we need to cool away. In the upper temperature region here, on a cryostat between 20 and 40 Kelvin, we have to control the thermal radiation heat losses by choosing an appropriate insulation depending on your design. And here's a typical example of how MLI looks like. And on the right graph, you see what optimal layer density of those stacked blankets you need to apply. So this is insulation, mylar substrate, and aluminium deposited on top of it. Now, the question always was really, how much high purity aluminium do I really need to deposit on a mylar foil to achieve good reflection? And earlier on, as we did not know it better, we thought 2 times 600 angstrom for the superconducting supercollider would be optimal, but now we found that it suffices if you use aluminium and you get the surface emittance that 2 times 400 angstrom is totally adequate for all radiation-related applications. So this slide is important as well. It shows an MRI magnet during assembly before closing it up, but note the big improvement is the foil performance here. We are now shielding with achievable heat fluxes down to less than 0.5 watts per square meter. So that has about 15 square meters in total and surface. And for 4K surfaces, we now have a single layer foil that's wrapped around the helium tank that has an emissivity factor of 0.004. That is what can be achieved now. It's a recent achievement. It's better or even equal to silver. It's a huge improvement thanks to recent advances in 4K foil technology. There are a lot of technology challenges at 4 Kelvin. And that is one which has been solved. Basically, we eliminated the use of silver. There are some advanced cryopaints coming up along from NASA, but those are not yet there yet with respect to the performance. Now, turning quickly to the most important cooling device in cryogenics, the so-called Cryo-Coolers, which is kind of a modular standalone cooling device. And this slide here gives you an overview of an estimate of which application would need what cooling power, depending on the temperature range. That's a very nice plot I got from Ray Radebow. Great improvement here, especially for high temperature superconducting applications. Here are some typical coolers you might find on the market from Cryomax, Sumitomo, and all. Some smaller systems here and bigger systems. And here's an overview of the current status of the advanced cryo-coolers. And this table actually allows you to choose from different coolers for the application you are targeting. And we have seen quite a big dramatic increase in cooling power at around 80 Kelvin. It's about 600 watt, and even bottom temperature is still 26 Kelvin. And for there is no cooling power at 26 Kelvin. We now shift gear again a bit to how we actually transfer heat from a warm end to a cold end in a cryosystem, and that's quite interesting because that's what we need to do all the time. We have to have kind of cold plates or heat buses, and this slide shows a very advanced way of achieving this kind of heat transfer, and that is by using pulsating heat pipes. And this is a technology that GE sponsored and initiated actually, and postulating it as an advanced way of transferring heat in large cryogenic structures. So here are the capillaries Here's a condenser and here's an evaporator. And that was a very early experiments to see what's going on. And I need to explain it a bit. So how does it now differ from standard heat pipes? On the left, we have the range. We do have the traditional heat pipes, 0% liquid. And on the right, the thermosiphon is about 90 to 100% liquid. And in between, however, there was a heat pipe liquid fill range that was never explored before until Conductor took care of it for room temperature applications. And now we can use this technology in cryogenics with a so-called large working zone, depending on your cryogenic design requirement. And if you look at the stochastic way bubbles move around a liquid capillary tube, actually one would never believe that there's an actually efficient heat transfer mechanism being established. And here I'm showing it again. On the left, we show the traditional heat pipe configurations for room temperature, but all of those heat pipe configurations are equally valid for the cryogenic regions. And the proposed pulsating heat pipes, or PHPs, are shown in the lower left. And with those new heat pipes, it is possible to achieve now thermal conductivities in the kilowatt range over the length of several meters. And this is really fantastic news. Here's a condenser and here's say evaporator over long lengths. And thanks to Maria Barber. And if you would not have those PHPs, you would have to go to aluminium with high thermal conductivity or high triple R ratio. And that is a very costly exercise. And besides that, PHPs give you an enormous benefit at temperature ranges where all metallic conductors have actually very poor thermal conductivity. Now, we not only need to transfer heat like we do with a heat press, but we also need to store cold. And what do I mean by that? Suppose you lose cooling power, or the use power of your cooler. What do you do then? You need to keep your cold mass cold to avoid any magnet quench. And it's a difficult undertaking, but very recently some good solutions have been found, as shown in the table, and also from MIT. And we are taking advantage here from an CP anomaly solid nitrogen, where we can actually store some heat without warming up the cold mass. Now let's quickly look at some new materials. In cryogenics and superconducting technology, we always need epoxy resins with many different, especially tailored properties. And this area, a lot of work has recently been done with very good results. And note that the low temperature column is empty here on the left, totally empty. But given the high thermal conductivity at room temperature here, of some very recent epoxy resin modifications, we can postulate there is great potential for them in the cryogenic domain. And it's everyone who's working on superconducting technology knows how important that is. However, the biggest impact and advance the cryogenics world is currently seeing is related to the latest progress in additive manufacturing. And to give you just one of many examples, here's an Inconel or titanium alloy-based gas gap switch for use at 1 Kelvin. And what you need to do here is, apart from understanding the whole manufacturing technique, is you need to learn more about the material, actual material properties you are using in additive manufacturing. And this new technology enables that, finally gives us low cost access to materials we never had a chance to use in cryogenics commercially. And this is especially true also for delicate heat exchangers of pure copper. And you can see here, this gap is here about 200 micrometer only. And it's a very convoluted structure to minimize the thermal conductivity in axial way. Now, before we close, let me just point out there's now an opportunity for the research community to test large superconducting coils in our new test facility. It's an in-ground vacuum chamber in 5 meter diameter and 7.5 meter long, where you are invited to test your superconducting test coils, and will be opening in 2023. There will be a cryo plant attached to it for easy and fast cool down. Now, to put a summary, on the advantages in cryogenics, very clearly, thermosiphon technology moved into nearly every superconducting application, from very small to large systems. Worldwide advanced development effort replacing expensive helium with hydrogen wherever possible. Cryogenics will definitely lead the way towards a global hydrogen economy. There is a big improvement in GM and PTR, pulse tube cooler cooling powers. There's a good efficiency increase in 4K dual stage coolers by 50% as compared to 1996. That's a recent improvement as well. And it's important because this is an increase of cooling power without an increase in compressor power. The dual stage coolers with 2.4 watts at 4 Kelvin are now available. There's a big increase in cooling powers for single stage coolers as well. Now we are up to 40 watts at 20 Kelvin, which is good for many cryogenic cold mass superconducting applications. And what's also helpful is that there are cryo plants, commercial, that provide several thousands of watts of cooling power at 8 Kelvin with a small footprint. But what we really need to do is we need to expand our materials testing capacity to capitalize on additive manufacturing opportunities. Yeah, because definitely new challenges here, new properties, and we, as I said earlier, we need to have a deep dive into technology of epoxy fillers and develop new epoxies for cryogenic use with superconductors. So here's my last slide. What are the future tasks for cryogenics? Hydrogen flights, that is going to happen, and it will take shape with the implementation of green hydrogen, infrastructure becoming available, and liquid hydrogen is going to replace conventional jet A fuel. We need to develop a bit on liquid hydrogen pumps and superconducting bearings. That is being done. We need to look at superconducting bus bars and transfer lines, low weight liquid hydrogen tanks, and especially hydrogen tanks that are linerless, and that requires big material development. Then a big thing is that materials research, we are really bad on that. We should invest a lot more money in materials research, and we still use data every day from the 70s, yeah? Because all this material research is very expensive. And as I said, development of new epoxy resins and carbon fiber composites, especially for liquid hydrogen tanks. And in general, cryogenics for large structures is not very well understood. It's okay for smaller systems, but as you go to larger structures, that is a challenge. So what is a new frontier? It's definitely the Mars missions coming up and the storage of 24 tons of hydrogen in spaceships and for travel in a microgravity environment. And we need to reboot all the efforts we already did in the past of establishing planetary superconducting technology. And there is also, of course, quite an interest in asteroid mining of mineral resources where cryogenics is badly needed as well. And If you find it interesting, please join the Cryogenics community, the Cryogenic Engineering Conference, the International Cryogenic Engineering Conferences, and the Cryogenic Societies. And I think that's the end of my talk. Thank you very much.
Thank you very much for your very comprehensive presentation. Question, please. We have no questions.
Hello, Wolfgang. Thank you very much for a very comprehensive presentation. I may have missed maybe. Do you comment on Mgb2? What is the future of Mgb2 in these cryogenics? Also.
Yeah, I think that's what I was trying to say. Maybe it wasn't that clear. Future of Mgb2 is great. Definitely, there are some applications where you really want to exploit the 20 Kelvin temperature range. That's what I was trying to show in one of these slides. There's a big advantage in cryogenics to go to 20 Kelvin from 4 Kelvin. There are applications, I can't really talk about it, related to ships where Mgb2 really does make a big difference because of the 20 Kelvin cryogenic environment. This is a big thing. And also for many other applications like aerospace technology, yeah, that's all Mgb2 based. It's not YBCO based. It's Mgb2 based. So the problem we have is Mgb2 is that we don't get enough wire. Yeah, and when you order Mgb2 wire, it takes at least 9 months before you receive your shipment, and that needs to change. I see, and we at GE, I can say that see a great potential on Mgb2.
I have a question. Are you here? Hello?
Sure.
Okay. I, those ultra low temperature like micro-Kelvin and belongs to your field of cryogenics, or is it very, very far from applications, or applications are still super far from now, or could you comment?
There are no real applications that is quantum computing. Quite touched that. There was not enough time to go into it. Yes, that's of course also a very important domain in cryogenics, but it's more low temperature physics, I would say.
Okay. Thank you.
Any other questions? Comments? If not, thanks.
Thank you very much. Bye-bye.